Hello, and thank you for joining today. My name is Derek Kane, and today we're going to get into the topic of exploratory data analysis and model selection. This lecture is part of a broader series of lectures related to predictive analytics, machine learning, and data science technologies. If you haven't gone through the previous lectures about installing RStudio and an introduction to business intelligence technologies, don't worry. However, for most of the modeling exercises and lectures that we're going to be going down the road, I think this is an excellent primer, and we should be comfortable with the concepts that are going to be discussed contained in this lecture. With that said, thank you, and let's begin. The overview of topics we're going to get into today is going to include an introduction to exploratory data analysis. What is it, and why should we be using it? We'll talk about some features of data sets and working with data for those who may or may not be familiar with data mining and statistical analysis in general. We'll get into the concept of data munging, which is cleaning and preparing the data for analysis. We'll dive into an overview of descriptive statistics, some of the measurements that are used in not only in the EDA, but for models in general. I'll also get into the topic of data transformations. Sometimes the data that we have doesn't exist in the format that we need to analyze it properly. So how do we go about working through these transformations? We'll get into the topic of variable selection procedures, and this will also include an introduction to principal component analysis. Finally, we'll talk about model selection procedures. What models should I be using for certain tasks that I'm trying to perform, and how do I go about knowing what the right model is for the right task? The law of the instrument, developed by Abraham Kaplan in 1964 and Abraham Maslow's hammer in 1966, state, if all you have is a hammer, everything looks like a nail. And I think this idiom makes a lot of sense in data science applications. There is no panacea for advanced analytics. Data scientists need to know what the correct tool is required for a particular task to be most effective and offer the proper solution. I like to use the analogy of a tool belt. So if I am a carpenter and I walk in a room and I see a nail that is protruding out of a board, I'm going to take out my hammer and I'm going to hammer in that nail. Likewise, if I see a screw that is loose, I'm going to first take a deep look at it, say, is it a Phillips head screw, is it a flathead, and then I'm going to pull out the appropriate tool and I'm going to address that situation. Data science is also very similar. We need to know, depending on the task in front of us, how to go about selecting the right tool and using the right tools. Whenever we engage in a predictive modeling activity, we need to first understand the data for which we are working from. This is called exploratory data analysis, or EDA. The primary purpose for the EDA is to better understand the data, how to transform the data if necessary, and how to assess limitations and underlying assumptions inherent in the data structure itself. Data scientists need to know how the various pieces of data fit together and nuances in the underlying structures in order to decide what the best approach is to the modeling task. Any type of method to look at data that does not include formal statistical modeling and inference generally falls under the EDA. Here are some of the main reasons why we utilize EDA. Detection of mistakes, checking of assumptions, preliminary selection of appropriate models and tools, determining relationships of the explanatory variables, independent variables, detecting the direction and size of relationships between the variables. I now want to move into the topic of understanding features of a data set. If you'll notice in front of you, we have a data set that is what I would consider to be a standard table. R uses the language data frame, but what's important about it is the structure, and we need to look at this carefully. We call the rows in this table observations. On the top, in the columns going across, we call these variables. And the variables in this case are price, lot size, bedrooms, bathrooms, stories, driveway, rec room, full base, etc., etc. One thing to notice is that in that top row, it's very cleanly showing these are the column headings. Then underneath, we see the actual values in our observations. Some of these variables are numeric in nature. The price variable, for instance, that's a numeric value. Others are qualitative, and they can also be referred to as categorical. These would be yes, no variables. It could be A, B, C, D. It could be a description of some form, classification schemes. So data sets contain a rich variety of sources of information, both quantitative and qualitative in nature. Let's take a look at our data set again. When we're modeling, we have to come up with the idea of what are we trying to predict. Remember, predictive analytics is looking at known information and trying to make inferences based off of known information to make predictions about the future. So it's using the data we already have available in constructing the model. And we call the piece of information that we're trying to model the dependent variable. In this case, I want to build a model that understands how price is developed. And by doing so, we're going to label this as a dependent variable. The independent variables are all of the variables which could be used to explain the dependent variable. Now, at this point in time, I think it's important to note that this is the entire pool of variables in consideration. We're not talking about our final model and the results of our work, but just the variables that we found that we want to assess whether or not they help us in explaining the dependent variable. Okay. So when looking at a data structure, we should have our dependent variable and we should have all of our independent variables in the data structure. There is a concept in working with data called data munging. And data munging is the transformation of raw data to a usable format. I use the analogy of it's like a cleaning process. Okay. Many data sets that we receive are not readily available for analysis. This is a very important consideration for people who strictly have an academic understanding of predictive modeling. When you get out in the real world and you start seeing the data sets that you have available, you're going to find that you might get a snippet of information from here, a snippet from there. We might not have a robust BI platform infrastructure in place to draw from, and the data that we have isn't really set up in a way that allows for effective model building. And we, of course, need to transform and clean this data. This process is often the most difficult and most time-consuming. You're going to spend an inordinate amount of time just getting the data, cleaning it, understanding it, and we can't take shortcuts here. Okay, if you take shortcuts here, your entire foundation of work is going to be compromised. So what are some of the data munging tasks that we're going to use? Data munging tasks include the renaming of variables, type conversions, encoding, decoding, and recoding data, merging of data sets, transforming data, handling missing data or imputation, and handling anomalous values. There are many facets to data munging, and it's an iterative process. It can occur at any stage throughout the overall EDA procedure and model development. So, as we're working, don't think of EDA as, okay, I've loaded my data, check, I'm going to perform my EDA, check, now I move on to model building, check, and going down the list. There are many times that you're going to build a model, you're going to produce some results, the results maybe aren't favorable, and then you might have to go back to your EDA and some of these data munging tasks. Okay. So it's iterative until you get the final model in place where you feel comfortable with. You might have to be drawing from these techniques over and over again. Let's go back to our example of understanding the data. And I've made some changes to our data structure just to kind of highlight some of the real-world situations we're going to see in the data. And this is important to start to get our detective hat on and really kind of looking at data from a critical standpoint. When I look at this data set, I see a number of issues that just immediately pop out to me. First, I see that in the price column that I'm missing values. What am I supposed to do with these missing values? Do I just delete the observation? Do I just continue on without it and just hope for the best? And we have to discuss, from a data management standpoint, what to do with this. In the bedroom field, most of these houses that are being sold, we can see bedrooms of 3, 2, 4, 5. However, I have one piece of data that has 15 bedrooms in there. Now, for a house that's $27,000, a 15-bedroom house, to me is just it's implausible. Now, I'm sure somebody could have a 15-bedroom house. I don't want to take that away from anyone if you do. But I think in the context of the problem that we're trying to solve, this would be a suitable candidate for what we would consider to be an outlier in the data, and potentially even a mistake in the input of the data. Our categorical and our qualitative fields here contain non-numeric information. So I have a blend of data between quantitative and qualitative. And I should consider, in this case, perhaps re-encoding the data and turning it into numeric values. However, in the rec room variable, one thing that does pop out is that I've got the number 7 in there. So most of the values are these qualitative, no, yes, and then 7 randomly appears. That clearly is an error of some sort. So when we're looking at data for the first time and trying to gain a sense of it, you can just do a spot check of the data and just to get a sense of structure, and then we can use other techniques in our EDA tool belt to kind of probe it a little deeper, and we'll talk about that in the upcoming slides. So let's spend some time now diving into the specifics of these data munging tasks. The first task we're going to talk about is the renaming of variables. The names of variables should make intuitive sense to non-practitioners, non-data scientists, just regular individuals, and they don't have to conform to IT protocols and standards. Well, what do I mean by this? If any of you have worked in a business environment and looked at the data from, let's say, an SAP ERP system, you're going to find that the naming conventions that are used for the tables that house the data are very technical in nature. I remember working in SAP, and one of the main tables is the Mara table, and the description of a field isn't too far off of the example that I have here, which is this T1K5X. Okay, well, what is that? To me, that doesn't necessarily add any value to the overall process. To an IT professional, this name could be very important because it can be part of the normalization of the database in other structures. But when we're doing our predictive modeling work and our data science work, feel free to change the name of that field, and there's no disadvantage of doing that. But just understand that when you're doing this type of work, if it's going back into an enterprise level system, that we have to be sensitive to how the IT group works with that data. Data type conversions. So depending upon the modeling task at hand and the software, the data might need to be expressed in a specific format in order to process correctly. So I have an example here of a column of information that contains a date. Okay, and if you look at it, it spells out nicely January 1st, 2014. In SQL terminology, this is a text string. Okay, specifically, it's what's called a varchar. However, in order to process this information using statistical methods, we have to ensure that the date and the values contained in the date field are in a date value type format. So there are times that just because it looks like a date or it looks like a number, it might not actually be in the right format, and we have to convert it into the appropriate format. Okay. So when you're looking at the data, take a look under the hood at the table structure and the types of values that are contained within, and just make sure that they're in the right format. And if not, understand that we're going to have to do some data type conversions. Encoding of data. There are times when we need to change the underlying contents in a variable to prepare them for analytics. So going from this qualitative measure to a quantitative measure. Yes, no in our driveway variable, for example, can be re-represented as a 1 for yes and a 0 for no. And by doing so and having a numeric value allows us to use many different methods to work with that data. So there are instances where we want to keep driveway as yes or no, and then there are instances where changing it to a numeric value offers value in the overall predictive model building process. For example, if we're using categorical variables, we need to clean them and get rid of non-response categories like I don't know, no answer, NA, etc. And we need to ensure that the encoding of categories, and potentially the reverse valence, to ensure that models are built and interpreted correctly. And what this means is, if I've got information that's set up in a Likert scale, so I strongly disagree, I disagree, I have no preference, I agree, and I strongly agree. That order is very important in how we encode the information. I don't want to have a value of 4 equate to strongly agree, and then a value of 3 equate to strongly disagree. That doesn't make sense. So no preference, for example, doesn't offer any value. It's neutral. So do I even want to include that when I'm going through my encoding of my data? So this little flowchart that I have here is showing that, okay, we have to reorganize the information into an order that makes sense, remove components that don't add value to the structure, and then encode the information based off of a numerical set that makes sense. Now, there are many times in data systems, and I've seen this behind the scenes, that let's say we're entering information about a customer, and the information about the customer might be their name, their address, and age, for example. Well, if we don't put a value into the age field and we leave that blank, assuming that the system doesn't force you to have to enter age, behind the scenes, we might sometimes see this as a null value, and other times we'll see it with a value of like 999, for example. Well, this age value of 999 is a numeric value. It's clearly false. I mean, nobody's 1,000 years old. It could just be somebody just with a fat finger just punching in 999 just to move through the prompt. But when it comes to building of models, this creates a problem for us, and we need to ensure that we're checking for these type of mistakes and encoding appropriately. The merging of data sets. Now, there are many different ways to go about manipulating data, but more often than not, I talk about this because we're not going to get the data in its pretty final form. We're going to have to get our hands dirty and work on merging these components together. Okay. So imagine if I have a data set here, and this data set is a very simple table. It has a unique identifier, a primary key, if you will, and then it has price and lot size, and it has some variables. And I've got another table with the same primary key and other pieces of information. Well, I can take this and I can merge them together into one comprehensive data set. And my personal preferences and the way I like to work is I like to do this type of work outside of the R language. I use a Microsoft SQL Server for a lot of my data manipulation, Microsoft Access, good old Microsoft Excel. I play around with the data, get it melded into its form, and then I pass it to the statistical software. You could very well do this type of work directly in a language like R. And there are many packages like the Plier package that help to kind of streamline that approach. Find the method that is most suitable for your needs and go forward with it, but be prepared to be able to manipulate data. And one observation here is that using the primary keys, we have to have a common linkage. So if you're trying to construct a VLOOKUP, for example, understanding the nuances of bringing data together will help you. Now, do we actually need the ID when we're building the model? No. In this case, we don't, unless we want to attribute it back to the ID. So we can blow out that variable, if it's no longer needed. So we might use information to help us get the data sets merged, and then when it comes to model building, only take the components that are necessary that help to advance the task at hand. The transformation of variables. This is a topic that we're going to get into in quite some detail later on in the presentation, but there are many times where a variable will need to be transformed in order to achieve linearity. Okay, and this aids in strengthening the results of parametric-based methods. So if I'm looking at a data set and I'm just showing a histogram here, and I don't want to get too much into the mechanics here, sometimes I need to transform the data. And when you run the transformation, it changes the shape a little bit into something which is more conducive for analysis. So a big part of the work that we're going to do is going to be looking at how the data actually is presented, and then we have to make assessments on whether or not we have to make adjustments. Imputation. This is the concept of handling missing values in a column. If there are missing values, we can't just leave them unattended. We have to decide how we want to handle it. What we can do is we can say, okay, I'm missing a value. I don't want this to influence my model building. Just remove the observation from the data set. That's one approach we can take. Another would be to calculate a value for this null, which is imputing. This usually is used with a measure of dispersion, such as mean or median. Typically, you'll see the mean. I've actually seen some successful approaches that get a little deeper, that actually draw from linear regression formulas, which to me is great. I mean, you can use a modeling technique to address data munging tasks. And in our example here, we're now showing our missing data, and then we have a data that has been placed in it using our measure of dispersion of mean. Handling of anomalous values. Depending upon the analytical task in front of us, we need to assess points which exhibit a great deal of influence on the model. If I'm looking at this model on the right-hand side, I have data points that form a nice diagonal line, and I have a regression line that is supposed to cut through those data points. But I have one point that sits on the top that is distinctively different than the rest of them. And understanding that data point is a critical component of the EDA in general. Okay. We can detect these through the use of scatterplots, and you can immediately tell when you have data points that fall outside of the normal spread. Now, many times we will delete this outlier. We'll say, okay, I want to build a model, a linear regression model. Let's go ahead and remove this observation. I don't want it influencing the quality of the model that I'm going to build. Some instances you can remove this and you can impute a value in its place. But when you do this, now we're talking about making significant changes to the data structure itself. And then you have to ask the question, if I'm going to begin that process, that's a slippery slope, and can I really trust the quality of my predictions that I'm producing by doing this? One important aspect that I really want to drive home, and this is from a business standpoint, is that there is something which is causing this data point to be an outlier. It's different than the rest. Why is this? If looking at the data and that particular observation, by doing so, allows for us to gain a clue for an efficiency or a breakdown in a process. New insights can be gleaned from outliers, and if we want to demonstrate value as data scientists, start by looking at the outliers and the factors that are driving them to be what they are. By doing so, can lead to a lot of advantages throughout an organization. I now want to spend some time talking about descriptive statistics. I'm not going to get into a very deep discussion of statistics in general, but more of an overview of some of the techniques that are important to consider when working with a predictive model building. And all descriptive statistics are is they describe the data in a qualitative or quantitative manner. They help us to provide a summary of the shape of the data, and the shapes of the data are very important when they're trying to decide how we want to go about modeling. These statistics help us to understand when transformations, imputations, removal of outliers are necessary prior to model building. Descriptive statistics are a collection of measurements of two things: the location and variability of data. The location tells you of the central value of your variable. The variability refers to the spread of the data from the center value. Okay, so these concepts are important to think about as you're walking through the next series of slides. Okay. And statistics is essentially the study of what causes this variability in the data itself. Now, I'm sure I'm dumbing down the the profession to a very simple statement here, but I think that captures the essence of what statistics really is. We're going to spend some time now talking about measurements of location. The first measurement is called the mean, and this is a measure of central tendency. The mean is the sum of the observations divided by the total number of observations. It is the most common indicator of central tendency of a variable, and it's a very powerful one to use. The median, to derive the value of the median, we need to sort the data from lowest to highest or highest to lowest, depending on your preference, and then we have to find the value of the number that sits in the middle of the data. This is called the median. The mode refers to the most frequent occurrence of a value within the variable. In our example, we see that the number 2 appears multiple times, and because it appears more times than the other, it's considered to be the mode. On the other hand, now we need to talk about variability and measures of dispersion. The variance is a measure of dispersion of the data from the mean. A standard deviation is the square root of the variance. This indicates how close the data is to the mean. And the range is a measure of dispersion. It is the simple difference between the largest and smallest values. Now that we've talked about these concepts, I want to begin shifting into a more visual approach to EDA. And one important tool that is used by data scientists and statisticians are the use of histograms. Histograms are a graphical display of data using bars of different heights. This allows us to evaluate the shape of the underlying distribution. Essentially, a histogram is a bar chart that groups numbers into ranges or bins. So imagine, if you will, I've got a variable that contains some data points of different numbers, 1, 2, 3, 4, etc. We take these numbers and, using SQL terminology, we're performing a group by of this column, and then additionally we're going to do a count of the values that are contained next to this group by statement. Well, when we do this and we plot it, we're essentially developing our histogram. And we can see that the shape in this case, for this example, is a pyramid-like shape. Okay. And that's really all histograms are. We can take the values and put them in bins, and all a bin is saying is take the numbers 1 and 2 together and combine them. So instead of having many bars, we can have a smaller number of bars. And we can change how the look of this histogram is presented. The data can be spread out or distributed in many different ways. When we look at distributions, it can be spread out more on the left-hand side, which are just more bins that appear on the left-hand side, or more on the right-hand side, which shows more bins on the right. Or it can be all jumbled up. We can look at this block of data and we don't see a discernible pattern. Okay, so when we're looking at the data, just make observations of what's the shape? How does the data actually look like? This topic lends itself very nicely to the topic of normal distributions. And there are many cases where the data tends to be around a central value with no bias on the left or right-hand side, and it gets close to what is called a normal distribution. A normal distribution is also referred to as the bell curve. And if you look at the shape of this histogram that we're showing, we see that it's not quite a perfect pyramid, and if you look at the line that's overlaid on top of it, that is the bell curve or the normal distribution. And it looks somewhat similar to the bell that I had put on the image on the right-hand side, And there are properties of this particular distribution that make it very useful in machine learning and predictive analytics. And we're going to tap into that in a lot of our models and approaches. So it follows closely to the bell curve from our histogram, but not exactly. There are many things that follow a normal distribution. For example, heights of people, the size of things produced by machines, errors in measurement, blood pressure, academic test scores, quincunx, or plinko if you're a Price is Right fan, as I am. When you drop the plinko down and it settles into the dollar value that you're going to get, whether it's 1,000, 0, or 10,000. If you drop enough of these plinko chips in there, you're going to find a normal distribution is going to produce as a result. So these are elements that are natural. Nature produces normal distributions if left to itself. We say that a data is normally distributed when the histogram has symmetry down the middle. The measures of central tendency, mean, median, and mode, are all reside in the middle, and 50% of the observations exist on the left-hand side and 50% exist on the right-hand side. So the mean, median, mode have to equal the same. We have symmetry, and the values are spread. When we calculate the standard deviation of the mean, we find that 68% of values are within one deviation of the mean, 95% of values are within two deviations of the mean, 99.7% of values are within three standard deviations of the mean. So within three standard deviations, we should encompass 99.7% of the overall observations if we have a normal distribution. And I said should, I mean we actually, that's the exact number. The number of standard deviations from the mean is also called the standard score or the z-score. So when I take data and I put it in a normal distribution, depending on the data that I'm looking at, it might be the age of individuals, it might be test scores as we've discussed. We can standardize this so when we're looking at normal distributions, instead of having to make a conversion each and every time, that we can apply a z-score and then just evaluate it using the z-score. Okay, so we can take any type of distribution and make this conversion. To convert a value to the z-score, we first subtract the mean, and then we divide by the standard deviation. Standardizing helps us make decisions about the data, and it makes our life a lot easier by only having to refer to a single table for statistical testing. This is a really excellent graphic that shows a lot of information and is worth spending some time to understand. If I'm taking all of my data, starting on the left-hand side of the distribution, and I'm walking to the right-hand side, we see the cumulative percent of observations. Okay. So as I get to different deviations from the mean, I can see the amount of data that has been covered. So for instance, minus one deviation from the mean, starting from the left-hand side, accounts for 15.9% of the overall observations. 0 deviations from the mean accounts for 50%, as we've talked about. 2 deviations from the mean is at 97.7%, and at various half deviation intervals we can see the cumulative percent. And in between each one of the deviations, so between 1 and 1.5, we can see how much data is being covered through that particular section. So if if you're looking at understanding normal distributions and the spread of the data, I think this is a helpful graphic. There are other moments about the mean, skewness and kurtosis, that can be used to understand what distribution should be used and when there are 3 or more parameters to estimate. So we can think of these normal distributions as kind of fluid objects. I sometimes think of them as kind of like jello molds. So if you look at the image on the left-hand side, for example, if we were to touch it and push it to the right-hand side, we would get that green shift, and that's a negative skewness. Okay, so instead of it falling in the center, it's now shifting the data to the right. Likewise, if I touch my jello mold and push it to the left, we're going to get a positive skewness, which is considered to be a left modal skew. At the same time, imagine taking the top of the distribution and pushing down on it or pulling up on it. If I push down on it, that is a measure of kurtosis. And if I pull up, that's a different type of measure of kurtosis. I want to talk a little more about the skewness side of it, and that's really referring to the lopsidedness of the distribution. If a distribution has a negative skewness, sometimes described as left skewed, it has a longer tail to the left than to the right. A positively skewed distribution, or right skewed, has a longer tail to the right, and zero skewed distributions are roughly symmetric. Okay, so we can look at these graphics here to kind of understand in certain skewed circumstances what the measure's central tendency will look like, and where the values will fall on the distribution. Here is the calculation for the skewness statistic for those mathematically inclined folks. And when you calculate this skewness statistic, if I have a value that is greater than 0, I know that I have a right skewed distribution. If I have a value that is less than 0, I know I have a left skewed distribution. And of course, if my skewness is equal to 0, then my distribution is symmetric around the mean, and it's a normal distribution. Let's spend some time now talking about kurtosis. Kurtosis is an indicator used in the distribution analysis as a sign of the flattening or peakedness of a distribution. The kurtosis is calculated from the following formula. Likewise, with our skewness statistic, we can interpret kurtosis as the following. If it is greater than 3, we have a leptokurtic distribution. The leptokurtic distribution is sharper than a normal distribution, with the values concentrated around the mean and longer tails. Okay, and what this implies is that we have a higher probability for more extreme values. On the other hand, if I have a kurtosis value of less than 3, I have a platykurtic distribution, which is flatter than a normal distribution with a wider peak. The probability for extreme values is less than a normal distribution, and the values are wider spread around the mean. Finally, if I have a kurtosis value of 3, I'm looking at a mesokurtic distribution, which is a normal distribution. And one way to think about these topics is through the images that I'm showing on the left-hand side. Platykurtic looks like a duck-billed platypus. So whenever I think of, the shape of a distribution, and I'm thinking about kurtosis and platykurtic distributions, just imagine this fun little animal, this chunky little guy sitting down there, and it will fortify the idea. Leptokurtic, on the other hand, has 2 kangaroos that are standing next to each other and looking at each other. And I believe the origin of the word leptokurtic is from lep, which is leaping, and the type of movement that a kangaroo would make. following table gives us some examples of skewness and kurtosis for common distributions. For now, all we've talked about is the normal distribution, but that's not the only distribution that exists when working with data. There are many others, and I just wanted to show in this table that you can calculate the skewness and kurtosis variables and understand what type of distribution I'm looking at. We briefly mentioned other types of distributions, and I just want to showcase a couple of them so that we're familiar with them when we're working through our data. Okay, so here are some examples of other common distributions we may encounter. On the left hand, we have a Poisson distribution, which to me it looks very similar to a roller coaster ride. You start on the left-hand side, it's a very steep incline, you're moving up to the top, and then it tapers down, similar to a normal distribution, but it has a very long tail on the right-hand side. So whenever you see a distribution that looks like this, know that you're going to be working with the Poisson. On the right-hand side, we have chi-square distributions, and depending on the degrees of freedom that you're looking at, the shape can be radically different. So this image shows that for a chi-square distribution of a degrees of freedom of 1, it has a very particular look. 2 has a different look. 3, 5, and 10. So as you're moving across the distribution, you need to understand how degrees of freedom play into this particular metric. We spent a lot of time talking about histograms, bar charts, and normal distributions. I now want to get into the topic of box plots. A box plot is a nice way to graphically represent the data in order to communicate the data through their quartiles. I didn't really use box plots a lot at first. I just thought, it's just another way of rehashing the same data. It's just, okay, I'm just showing graphics for the sake of showing graphics. But since then, I have a newfound appreciation for them. They convey a lot of information in a very condensed form and are extremely helpful when trying to gauge the size and shape of distributions. And the way to think of a box plot is through the example I have on the right-hand side. So I have a normal distribution on the bottom, and I'm putting a box plot on top of it that matches a normal distribution. The box represents the two central quartiles, okay, from the mean. The green line shows where the mean exists within that box of quartiles. Then I have whiskers that push out both to the left and to the right, and then a distinct edge. And the edges represent the upper and lower whiskers, and each of the lower bound of quartile of group 1 to the upper bound of quartile of group 4. Now, if I'm looking at a right-skewed distribution, and I'm evaluating a box plot of it, this is what I would see. I would see a very small tail on the left-hand side. The middle section, might have my measure of mean directly in the middle of the line, being in the middle in this case. A very long whisker to the right-hand side, and then data points that are beyond that whisker. And those points essentially are outliers because they fall outside of the fourth quartile group. So when we're looking at different distributions, the shape of the box and whisker plot can be used as a nice gauge. Now that we've discussed box plots, histograms, bar charts, I want to move into another very important tool in the EDA toolkit. These are scatterplots. And what a scatterplot is it's a point plot between two variables used to understand the spread of data. The spread of the data allows for us to understand if the data has a nonlinear or linear relationship and the relative degree of correlation in the data. This technique can also be used to detect outliers in the data. A scatter plot becomes more powerful when we incorporate categorical data as an additional dimension. So if I'm looking at the scatter plot on the right-hand side, I see all these little point estimates. And in this case, I'm just comparing two independent variables in this data set. Okay, I'm looking at petal width and petal length of the iris data set. And you can see that most of these points follow a linear pattern. We can see through how close they are to the line. But when we add the classification, okay, so what are the different types of plants or flowers that we're looking at here, we see that, represented by colors, that they form very distinct pockets and bands of them. So a scatter plot, you can just compare two different variables against each other and get a lot of value, but by adding additional dimensions allows you to see more. Scatterplot matrices can offer a 10,000 feet view of the patterns within the data. So we can run a bunch of scatter plots at the same time. If we have all numeric values in our data set for our independent variables, or even our dependent variables, we can produce this scatterplot matrix and just see the relationships of the data. When two sets of data points are strongly linked together, we say that they have a high correlation. Correlation is considered to be positive when the values increase together, and correlation is considered to be negative when one value decreases as the other increases. Correlation can have a value ranging from 1, which implies a perfect positive correlation, to 0, which implies that there's no correlation in the data whatsoever, to -1, representing a perfect negative correlation. And I want to spend a little time looking at these correlations as they relate to the scatter plots we had just talked about. If you look on the upper left-hand side of our graphic, we see a perfect positive correlation. There's clearly a linear relationship in this data. All the data points neatly form a line, and I can draw a line directly through that data set. It is perfectly positively correlated. The second one, the 0.8, if I was to draw a line in between those dots, not all the points would fit directly on this line. They're very close. I can tell that they're all moving in an upward direction, but they're not as compact as we saw with a perfect positive correlation. If I move to the right to a low positive correlation, or the 0.3, I find that the data still is moving in a general upward trend, but the spread is now even wider than at the 0.8. This then leads us to a correlation of 0, that if I was to draw a line, you would see that the line doesn't make sense. It doesn't really fit the data very well. Likewise, if I start shifting now from 0 into the negative value, I can see the influence that a 0.3 has compared to a 0.8, and then ultimately forming that nice line at a -1. So correlation can take different types of values depending on the shape of the data. One of the most important concepts to understand in predictive modeling and machine learning in general is this statement right here. Correlation does not imply causation. And what does that mean? So just because I have two data points that exhibit a correlation with each other doesn't mean that they're causally linked. So if I slip on a banana peel in the middle of the road and the stock market goes up 100%, and depending on my degree of slipping, I can see a relationship between the movements of the stock market, I can't make the statement that my slipping on a banana peel is causing the stock market to move. It may be correlated, but my slipping a banana peel really, in the grand scheme of things, doesn't have an effect on a business in China. So we need to be careful when we look at correlations and not to assume that a strongly indicating correlation implies, a causal relationship. And we need to think about this in all predictive analytics, all statistics, all machine learning. Just because we have correlation does not imply causation. So we can take all of our correlations and form a correlation matrix, which is just a numerical representation of the variables and their relative correlations. I find this kind of hard to look at after a while. I mean, some people like to look at the data. I prefer more visual methods. So in our language, we have ways of showing heat maps of correlations. So remember, when we have data that is more closely linked, closer to the 1 or to the negative 1, they're going to be better for our model building. So these variables are going to help us in explaining the phenomenon that we're modeling. We need to be careful about assuming that lower correlation intervals are potentially poor variables for model building. And this is an important concept for us to understand as data scientists. I don't want to look at a correlation and say, oh, it's 0.8, that means it's great. Or 0.4, I don't think I should use this because, it's not as great as a 0.8. Evaluation of correlation values should be handled on a case-by-case basis for modeling. And the reason I bring this up is it depends on the application of our predictive analytics. For example, in behavioral sciences, it is not uncommon to have correlations between 0.3 and 0.4 for statistically significant variables that have been evaluated in literature review. So, understanding complex systems such as human behavior, we're not going to find data that it nicely fits, at very high degrees of correlation. So it is perfectly acceptable in this application to be looking at lower correlation. I want to spend a little time looking at a very powerful example that kind of fortifies the need to look at data in order to model it correctly. This example is what's called Anscombe's quartet. And if you look at all 4 of these charts here, you're going to see that they all, from a data point standpoint, look distinctively different. Okay, one of them on the top left-hand side looks like a loosely correlated upward trend of data points with a line that cuts through the middle of them. The second one to the right of that shows a curvilinear type shape. It's not a perfectly linear format. It's nonlinear in its nature. But nevertheless, we have our line that just kind of cuts through 2 points, and it doesn't really model it very well. On the bottom left-hand side, we have a data point that is an outlier, and we can see that our regression line is no longer cutting through all of the data points as it could because it's being influenced by that outlier. And to the right, we have another example where all the data points form a straight line, and we have one influencing outlier all the way on the right-hand side. What's interesting about this are all of these regression lines that we're looking at are exactly the same thing. They have the same models and same coefficients. These models have identical mean, variance, and correlation values, even though their spreads are wildly different. So that's one thing to consider, that just by looking at the numeric values and trying to derive sense and meaning out of it can get you only so far. You also need to rely on visual cues to make assessments of whether or not what you're doing matches the data that we're looking at. Some of these models will require transformations in order to achieve linearity. Others have outliers that influence the performance, and we can address those in our data munging tasks. We've spent a lot of time talking about the data munging and transformations of variables. I now want to get into the concept of transformations. So when we're looking at data, we can understand when they're relevant and how to go about transforming them. So let's take a look at this particular scatter plot. This is our curvilinear relationship. We see that a nonlinear relationship exists between the dependent and independent variable in this case. When we see this example, we can make a transformation to achieve linearity. This is vital for models which require linearity. For instance, a linear regression analysis. Here are some types of transformations which we're going to go over. We'll talk about the power function and the exponential function in detail, but there are other transformations such as the polynomial function, logarithmic function, square root functions, and so on and so forth. I think the best way to understand transformations is to just look at the shapes of certain standard transformations. So if I plot my y variable against my x variable, y in this case is my dependent variable, and the x variable is my independent variable. And when I run a scatter plot of these points, do they take some of the shapes that I'm outlining here? If they do, then I know in order to achieve linearity, I can draw from mathematics and I can make a transformation. So the reciprocal function, it starts by shifting downward, and then it kind of tapers off as it goes down and flattens out as the values of x increase. Well, if that's the case, then we can use a reciprocal function. Okay, we can leverage our knowledge of the mathematics and calculate a transformation that will turn this shape into a straight line. If we have a square root function, we will see that it almost is parabolic in shape, okay, but it's just kind of very softly curving as it moves upwards. If I take a logarithmic function, for example, we see that it is a much rounder shape than our square root function. On the other hand, a power function, we see that it grows in a very linear way, but it's not quite a straight line. And a more extreme version is the exponential function, which we see starts very flat and then just grows exponentially. Let's take a little time now to talk about the power function and walk through a practical transformation example. So a power function takes the following form: y equals a times x raised to the b. It's important to note that the location of the variable x in the power function. Later in this activity, we will contrast the power function with the exponential function, where the variable x is an exponent rather than the base as in the equation. When I look at these points on this graph, it could be argued that the data is somewhat linear, showing a general upward trend. However, it's more likely that this function is nonlinear due to the general bend. So we need to come up with a way of fitting a model to this data through the use of a transformation. Let's get into a discussion of how to perform the transformations using the power function. First, we need to look at our function, which is y equals 3x squared. And what we want to do is we want to take the logarithm of both sides of this power function. The base of the logarithm is irrelevant. However, log x is understood to be the natural logarithm base e in the R language. That is, log x is equal to log ex in R. So when we do this, we now have log y equals log 3x squared. The log of a product is the sum of the logs, so we can rewrite the expression as follows. And another property of logs allows us to move the exponent down in the following manner. So instead of it saying log x squared, we can now say 2 log x. Let's take a look now of a method that we can use to prove out our power function. I'm going to create a regression formula in R that is going to take the log of y as a function of the log of x. When I run this, I see that my value of the intercept is 1.099 and my value of log of x is equal to 2. The slope in this case is 2, which is the slope indicated in our log y equals log 3 plus 2 log x. Supposedly, the intercept should be log of 3. So if I just take the log of 3 in R, I find that the value is 1.098, which is the same as the intercept we see on our regression formula. And when this happens, all the data points now, if I graphically represent them, will show a straight line as a linear relationship instead of the nonlinear relationship. What's important is that if the graph of the logarithm of the response variable versus the logarithm of the independent variable is this straight line, then we should suspect that the relationship between the original variables is that of a power function. And when we apply our model now to this y equals 3x squared using our log y equals log x, we see that the data now fits appropriately. Building off of our power transformations, here is a box plot representation of salaries for 500 employees at a university. So if I'm looking at this box plot, I can get a sense for the shape of the data. Well, what is the shape of this data set? It depends on what you're looking at. If we look at the middle 50% of the salaries, it looks very symmetric. The green line is directly in the center. There's symmetry on both sides. On the other hand, if we look at the tails and the portion of data beyond these quartiles, it's clear that we have a right skewness and a high number of outliers. One would expect to find a few large salaries at a university. Just because the data isn't in a normal distribution doesn't mean that it's invalid. If I'm looking at employees of a university, I would expect the outliers to appear to be the highest ranking officials. It could be the board of trustees, it could be the president of the university, or the department heads, for example, and the professors and the normal staff on hand to keep the facilities up and running would fall within the box and whisker plot. So this isn't uncommon by any means. However, if I want to take this data and transform it using our power function, I'm going to use a transformation of 0.3. Well, when I transform it, I see that I now have a more normal distribution. However, my measure of central tendency is now skewed a little bit. It's no longer that nice green line in the middle. It's shifted more to the right-hand side. We've controlled for the outliers, which is great, but the data now is different. Well, what have we learned from this exercise? For some data, it can be difficult to achieve symmetry of the whole batch. Here, the power transformation was helpful in making the tails symmetric, and control for the outliers, but it didn't symmetrize the middle salaries. In practice, one has to decide on the objective. If we're focusing on the middle part of the salaries with our predictive models, well then no re-expression is necessary. But if we want to look at the whole data set and control the outliers, then perhaps the choice of a power equaling 0.3 is a better choice. So we have to think about transformations and trying to achieve linearity in context to the problem at hand. How did we know to use a power function of 0.3 in the power transformation example? The statisticians George Box and David Cox developed a procedure to identify an appropriate exponent, lambda equaling 1, to use to transfer data into a normal shape. So why not 0.4 or 0.5? What makes 0.3 so special? The lambda value indicates the power to which all data should be raised in order to make this transformation. In order to do this, the Box-Cox power transformation searches from a lambda of -5 to a lambda of +5 until the best value is found. So it's a real powerful procedure in identifying how to achieve linearity in a data set. Here's a table which indicates which linear transformation to apply for various lambda values. So if I have a lambda that falls within a -2.5 to -1.5, perhaps the transformation I should use is an inverse square. If I have a value of somewhere between 1.5 to 2.5, maybe I should use the square value. So we can look at different lambda values and know, okay, from this value how I should go about transforming my data. Another important aspect of EDA is the use of residual plots. Typically, a residual plot is used for model evaluation, but I want to discuss it in the context of EDA here. And a residual plot is a scatter plot of the residuals, which is the difference between the actual and predicted value, against the predicted value. A proper model will exhibit a random pattern for the spread of the residuals with no discernible shape. So I have this imaginary line cutting through the middle, and I should not be able to visually detect any pattern. So when I'm looking at the spread of data here, I see that it's just kind of floating above and below the data with no real discernible shape. The residual plots are used extensively in linear regression analysis for diagnostics and assumption testing. For our purposes, in the EDA, they can actually help us to identify when a transformation is appropriate. For example, if we take a look at the graph on the bottom and we see that our residuals show a curved type pattern, well then we know that transformation will be necessary, and we can explore some methods like the Box-Cox transformation we had just described. I wanted to take a little time to create a transformation guide to help aid with the process of deciding when to use transformations to achieve linearity and how to evaluate it. Transforming a data set is a multi-step trial and error process. And this is just a general guideline that you can use to help you when you're confronted with this issue. The first step would be to conduct a standard regression analysis on the raw data. Don't do any linear transformations whatsoever. Construct your residual plot. If the plot pattern is random, don't transform the data. If the plot pattern is not random, continue going through this process. Then I would compute the coefficient of determination, and we'll get into that a little more in regression diagnostics in the next presentation. But for now, we're just calculating this metric. Then we choose how we want to transform the data. This could be our Box-Cox transformation, or we can look at the shape, make inferences on our own, but we're going to transform the data in some manner. We transform the independent variable, dependent variable, or both, depending on what we want to do. Then we conduct a regression analysis using these transformed variables. Afterwards, we compute the coefficient of determination based on the transformed variables. If the transformed r squared is greater than the raw score r squared, then the transformation was successful. Congratulations. If not, we're going to go back and repeat the process and try a different transformation method. While this isn't a foolproof approach, this is one approach you can adopt when working with the transformations. I now want to shift gears and talk about variable selection methods. How do we approach a modeling task when we have hundreds or thousands of independent variables? What if there are a significant number of variables with low correlations? So imagine a data set that just has an ungodly amount of variables. How do we work with this? Which ones do we include in the model? Are we going to build a model with 100 variables? That doesn't seem like it would make a whole lot of sense. Before we perform this work, we need to talk about the concept of dimensionality reduction. Dimensionality reduction is the process of reducing the number of variables under consideration and can be represented in feature selection and feature extraction approaches. Feature selection is a methodology that attempts to find a subset of the original variables using some form of selection criteria. These approaches are primarily through filtering, which is an example of which is information gain, and wrappers, such as search guided by accuracy. On the other hand, feature extraction is a transformation of the data in a higher dimensional space to a space of lower dimensions. A linear approach of feature extraction is called the principal component analysis, which we'll get into momentarily. Before we dive in on that topic, I just want to take a look at a way of understanding what feature extraction is actually doing in simple terms. If we look at the gargoyle picture that we have in front of us, we can tell that this gargoyle is a three-dimensional object. We can see the shape of the statue, we can see patterns in the wings. It's three-dimensional. Now imagine if I take this three-dimensional object and I smush it down to a circle that is in 2 dimensions. If I look at the image of this gargoyle smushed down in the 2 dimensions, I can still see features. I can see the face of the gargoyle in the middle of it. Now, the data is distorted, and the information might be distorted a little bit, but we're able to take information from a higher dimensional space and represent it in a lower dimensional space in order to take advantage of working with the data in different manners. When attempting to describe a model containing dependent and independent variables, it is desirable to be as accurate as possible, but at the same time to use as few variables as possible, and this is called the principle of parsimony. To help us find models of lesser amount of variables, there are some automated techniques that we can use, one of which is a forward selection procedure, and this is helpful in linear regression model building. And what this does is it first starts with a model that has no variables included. The term that adds the most value is identified and added to this model. The remaining variables are analyzed and the next most helpful variable is added. This process continues until none of the remaining variables will improve the model can be added. On the other hand, a backward selection procedure starts with all of the variables included in a model and then proceeds by sequentially removing variables one by one that improve the model until being deleted, until no additional deleting of variables will improve the model. A third approach is a hybrid, and it's called the stepwise selection procedure. And it starts very much like a forward selection procedure. After adding a variable to the model, then a backwards selection procedure is run on the existing variable pool within the model to try to eliminate any variables. So we add one variable and then we try to remove one, and this creates the telltale distinct stepwise pattern that we're talking about. Here is an example of a stepwise selection procedure which contains a large number of independent variables. After the routine has completed, note the variable list has been reduced. So if we look at our initial model, in this case, we have mileage as a function of price, make, model, trim, type, cylinders, liters, doors, cruise control, sound, leather, lots of variables. After we've run the procedure, our model now is much more compact. Okay. The variables which were removed did not meet a certain statistical confidence level. It didn't have an appropriate p-value, which we pre-specified. Unless we have specific subject matter expertise and expert-level knowledge of the data set at hand, we should set this p-value as 0.05 or smaller. So when it comes to these automated selection procedures, let's try to align our processes with statistically sound research. We don't have to. We can change and flex these parameters as we see fit. But if we're just starting out and learning how to use these models, let's start with 0.05. I now want to talk a little bit about principal component analysis. And this has always been a tricky subject for me to understand until recently. And I hope I can explain it well here. What principal component analysis procedure does is it takes a number of variables and it reduces them down to a smaller number of variables, which are called components. In our example, we're going to look at a number of variables: price, software, aesthetics, and brand. And from this, we're going to create 4 components. So I have my 4 variables here, and ideally we would pare this down to a smaller number of components, but we're going to create 4 components off of this. So when I run the principal component analysis in R, this is an output of what I see in the software. I have the importance of components and labeling component 1, 2, 3, and 4, and I have some information related to them. What is important to understand is the cumulative proportion. If I look at principal component 1, I find that my cumulative proportion is 0.607. If I look at component 2, I find my cumulative proportion is now 0.84. And if I go to component 3, it's 0.96, up to my last component, which gives me 1. And what this value is representing is how much information is retained through the reduction of our variables to the smaller components. So the cumulative proportion figure of 0.847 for component 2 tells us that the first 2 components account for 84.7% of the total variability of the data. Generally speaking, 80% accounts for the data rather well. The loadings can be thought of as new variables which have been created for our analysis. If you look at the loading figure below, for component 1, we have different values for price, software, aesthetics, and brand. And these are sub-equations you can think of. So if I'm interpreting the first component, the way to interpret it is taking 0.523 times the value for price plus 0.177 times the value for software minus 0.597 times the value for aesthetics minus 0.583 times the value for brand. By plugging in the values of each variable here, I now create my value for my principal component. I'm showing an example of some R code here to show how you can leverage principal components in an R model. So this is a logistic regression model that I'm using, but what's important is after the GLM in the parentheses, we have our dependent variable, OS, and we have our independent variables, which are now these principal components. And the syntax that I'm writing here of the PCA $scores bracket comma 1 end bracket plus comma 2 is representing principal component 1 and principal component 2. And I can build predictive models off of these principal components. Once we have the data in the proper format, before we perform any analysis, we need to explore the data and prepare it first. All of the variables are in columns and observations are in rows. It's a complete structure. We have all the variables that we need for our model building. There's at least one variable with a unique ID. We should also have a backup of the original data set handy. So when we're modeling, we don't want to touch the original data. We want to touch a mirror image of it, if you will. Sometimes when working in predictive analytics and machine learning, we can perform iterations on data, and we just want to make sure that we're not compromising our source. And we most certainly need to ensure that we've properly addressed any of the data munging tasks we've discussed in detail. An important aspect of predictive model building comes down to how we work with the data set. Okay. We need to split this data set into what's called a training and testing data set. And there are other techniques that can be used. But the idea behind it is that we want to build our predictive models against a training set, and then we want to evaluate them against the test set, which was not part of the model's original construction. To accomplish this, we randomly select observations for the training data set and the remaining into a test data set. And the question often is, well, how much should I put in a training data set versus a test data set? A lot of people give you the answer, it depends. And as you become more proficient with model building, you'll start to understand the trade-off between the two. And I'll talk about the trade-off in detail in our decision tree tutorial. But for now, I think a general rule of thumb is start with 70% for the training and 30% for the test. So if I'm looking at this data set, in this case, we can just think of, I'm just going to take a chunk of observations, pull them out, call them the training set, and I'm going to take another chunk and call them the testing set. In our previous example, we had decided to use a split of 70% for the model building and 30% for our validation set. Well, the more data that we spend on the training set, the better estimates that we'll get, provided that the data is accurate. Given a fixed amount of data to spend or cash in our wallet, too much spent in training won't give us a good assessment of the predictive performance. We may find a model that fits the training data very well, but it's not generalizable, okay? And we run into the problem of overfitting. If we spend too much In testing, we can't get a good assessment of the model parameters. Many business consumers of predictive models emphasize the need for an untouched set of samples to evaluate performance. They like this concept of a distinct training and testing set, but there are also other ways to go about it, using more statistical, robust methods. Overfitting occurs when a model inappropriately picks up on trends in the training set that do not generalize to new samples. When this occurs, assessments of the model based on the training set can show great predictive performance, but isn't reproducible in future samples. Some predictive models have dedicated knobs to control for overfitting, so you can calibrate certain features of predictive modeling algorithms to help address this issue of overfitting. The neighborhood size in a k-nearest neighbor model is one example. The number of splits in a decision tree model is another example. Often, poor choices are made for these parameters and result in overfitting. So if you don't understand the nuances of working with these algorithms, you should consult with statisticians and data scientists on how to best approach the tuning of certain models. This is a very simple example to show visually what overfitting is doing. So if I have a data set here and I'm going to produce two different models, the first model is going to show data that is using a very large amount of our spend in our training set. And we can see that it is capturing all of the data points with our predictive model. But if I apply new data to this set, the performance is going to be much less because the data points aren't going to sit in this distinct pattern. On the other hand, Model 2 shows that we're spending not enough in our training of the model. And we see that only a portion of it is covered by our predictive model. One obvious way to detect overfitting is the use of a test set. The predictive performance measures that we use to evaluate the performance should be consistent across the training and test set. However, repeated looks at the test set can also lead to overfitting. And what we're talking about here is if I've got a model that predicts, let's say with 90% accuracy in the training set, and then I go to a test set and apply the same model and it's 40% accuracy, that giant drop-off between both data sets is an indication of overfitting. However, depending on the way that we apply the model to the test set and through repeated approaches to this actually can lead to overfitting in and of itself. Resampling the training samples allows us to know when we are making poor choices for the values of these parameters. So we're not going to use a test set for certain models. Instead, what we're going to do is we're going to build our models off of the training data set, which contains 100% of the data. Resampling methods try to inject variation into a system in order to approximate the model's performance on future samples. We will walk through several types of resampling methods for training set samples. One such example is called k-folds cross-validation. And what k-folds cross-validation is doing is we're randomly splitting the data into k distinct blocks of roughly equal size. So if I look at the image on the left-hand side, I cut the data into a 60% split, 40%. So 60% I'm going to build my model off of, and I'm going to predict on 40%. Then after I do this, I then take my original data and I select a different set of the 60% and predict on a different set of the 40%. And I continue going about this process. Okay. And as I'm continuing, I continue until I get to the k-folds, until I've addressed all of the held out blocks. Then the final performance accuracy is based on the holdout predictions across all k-folds. Usually, the value of k is something between 5 or 10, and we leave out one cross-validation as each sample as a block. So if you're going to do a k-fold cross-validation, generally use between 5 and 10. Another technique is called repeated splits. In this case, we're going to take a random portion of our data, say 60 or 70%, and we use it to train a model while the remainder is used for prediction. This process is repeated many times, and then we take an average of the overall performance. Okay. These splits can also be generated using some type of stratified sampling technique. And we continue and repeat this process over and over through many iterations, generally somewhere between 20 and 100. And through the averaging, we find that the procedure has a smaller variance than k-fold cross-validation, but it is likely to be biased. Bootstrapping is another valuable technique, and what this does is it takes a random sample of the data with replacement. So we take the original data set, all 100%, and we randomly select a subcomponent that we're going to predict on. We built the model with all of the data and then apply it to just the data that we've held out. Okay. And we repeat this process over and over and over. Now what's interesting is that samples may be selected more than once, and each sample has an approximate 63.2% chance of showing up at least once. Some samples won't be selected, and these samples will be used to predict performance. The process is then repeated multiple times, let's say somewhere between 30 and 100 times. And what's nice is the procedure has a low variance but non-zero bias when compared to k-fold cross-validations. So all of these techniques have their pros and cons. It just depends on how we want to go about developing our models and evaluating them. We think that resampling will give us honest estimates of future performance, but there's still the issue of which model to select. One algorithm that we can use to select predictive models, and this comes from Max Kuhn, who is the developer of the Carrot package in R, and really a great statistician, and I've been using some of his material throughout this lecture. But he gives a very simple algorithm that we can go about for selecting the predictive models. So we hold out specific samples, we fit our model on the remainder, we predict the holdout samples, and then we calculate the average performance across these holdout predictions, and from there we determine what the optimal set of parameters that we should be using. We spent a lot of time talking about EDA variable selection procedures. I now want to take the opportunity to dive into selecting the right algorithm for the right task. We can think of predictive modeling in three broad categories of activities that we perform, and we need to understand how each modeling activity we're performing corresponds to each one of these buckets. We have predictive models, and predictive models are models of the relation between the specific performance of a unit in a data set and one or more known attributes or features of the unit. The objective of the model is to assess the likelihood that a similar unit in a different dataset will exhibit the specific performance. This is a very technical description, but we want to essentially have a data point in our data set as a dependent variable. We want to look at independent variables and make predictions that we think the dependent variable will showcase. And those type of approaches are predictive models. Descriptive models, they quantify relationships in data in a way that is often used for classification and clustering purposes. Unlike predictive models that focus on predicting a single customer behavior, such as a credit risk, descriptive models identify many different relationships between customers or products. Descriptive modeling tools can be used to develop further models that can simulate a large number of individualized agents and make predictions. So these are the classification type models. Decision trees are a form, even though they have predictive capabilities. But taking groups of data points and understanding how they relate to each other are part of the descriptive modeling process. Decision models describe the relationship between all elements of a decision, the known data, which includes the results of predictive models, the decision at hand, and forecast the results of the decision, in order to predict the results of decisions involving many variables. These models essentially become the basis of optimization techniques, and optimization really is maximizing certain outcomes while minimizing others. I want to take a step back and just look at a very simple example here. If the goal of the activity is to predict a value in a dataset, we need to first understand more about the dataset to determine the correct tool or approach. Let's examine this following dataset. Our goal here is to predict the price of a home based upon the lot size and number of bedrooms. Notice that there's no time element in this dataset. The price variable is called the dependent variable, and the lot size and bedrooms are the independent variables. For now, let's focus our attention on understanding the characteristics of the dependent variable. The house price variable seems to fall into a range of values, which implies that it is continuous in nature. So a house price can be $45,000, it can be $55,000, $600,000, $6 million, so on and so forth. It's definitely not a binary variable, and a binary variable is one which takes a value of a 0 or a 1. It can be one of two states. And an example of this would be, will they purchase a house, yes or no? A qualitative variable is one which has multiple layers and could be a description of a product. It could be product A, B, C. What type of house is it? Is it a large, medium, or small? So we have to understand which bucket does our dependent variable fall in. If we know we have a continuous variable, then that opens up a certain set of model algorithms that we can use. In this case, we can use linear regression, we can use CART models, and we can use neural networks. Now, because this data set does not have a time component, we probably wouldn't go about using a time series model. It's not the appropriate tool for this task. However, if I have a continuous variable of interest and time dimensions, okay, well then time series is back on the table. If the dependent variable was a binary response, a yes-no variable, there are a number of different methods that we would consider using. We could use logistic regression, survival analysis, neural networks, naive Bayes, decision trees, support vector machines, k-nearest neighbor, and the list goes on and on. If we need to classify or cluster variables together beyond a dichotomous variable, we can use some of the following descriptive techniques. So we can use association rules, we can use neural networks, naive Bayes decision trees, support vector machines, random forest models. And what's interesting is now we're starting to see some of these algorithms cropping up in multiple areas. We can use a neural network for continuous values. We can use it for dichotomous 0-1s. And we can also use it in a descriptive capacity as well. However, the flexibility of a neural network, the trade-off for the flexibility comes down to interpretability. So this is a class of algorithms that can be used in many applications, but there are also features of these algorithms that may be less than desirable. And we'll get into that as we're going through the series of lectures talking about specific nuances of these various techniques. I think it's important to have a general modeling strategy. There is usually an inverse relationship between the flexibility of a model and the power of the model and how easy it is to interpret. In the best case scenario, we want a parsimonious and interpretable model that has excellent performance. So a very simple model that can easily be explained, that just predicts with 100% accuracy. Unfortunately, that's not realistic in the predictive modeling world. There is a trade-off. If we want higher predictive performance, the trade-off is going to be we're not going to be able to understand it. Or we might understand it, but a general business user isn't. So a recommended strategy when approaching predictive modeling problems would be the following. Start with the most powerful black box type models that you can come up with. So your ace in the hole, your strongest algorithm. Get a sense for the best possible performance that you can get using that algorithm. Then go down and try to fit more simplistic, understandable models. Use a decision tree. Then evaluate the performance cost of using a simpler model versus the black box technique. So, is the knowledge gained by using ensembling methods, for example, a very complex system, better than being able to explain what the decision tree is doing to a general audience? And we need to know for the task at hand, what that performance cost is. So I think this is a nice general strategy that you can go about in building your predictive models and approaching predictive analytics.